Good morning, chemistry friends. Welcome to Friday. Most of today is just going to kind of be a work day, and really we'll go through the weekend with a work day, and Tuesday kind of a work day. We did shift our schedule a little bit as we took that one day so you could review your last exam. So, and then hopefully you've turned in most of you have turned in your pH homework. I've looked over some was good, some was errors. I'll get a key up over the weekend or by Tuesday so you can kind of look and see where you might have made errors, and you ask questions and stuff along doing those pH calculations. And then there'll also be, along with this today, I'm just going to give you a small worksheet with just a few problems on it, nothing much to take over the weekend with today's stuff, and give you really kind of Tuesday to work on it and clean up stuff. And we'll have another cleanup day next week as I'm kind of looking at the schedule and getting things wrapped up. There's some differences between when our seniors get the last of their knowledge and we prepare them for moving on, and our juniors. So there's a little bit of stuff going on there that has to be kind of rescheduled a little bit, and just rescheduling because they have been trying to, it took a little bit to kind of tweak when should the last day for new learning be, so that with this whole online extravaganza, things can be done with minimal stress, although stress is always there. When we last left you on our last film, we went through dissociation and how to look at a strong and a weak acid, and did one simple problem where you knew everything. All you had to do was set up the equilibrium constant, the dissociation constant formula, and then plug in all the concentrations. And where we're moving today is, I asked you this: what if I only know the initial concentration of the acid and nothing about equilibrium? How does that change things? Well, unfortunately, for those of you who don't necessarily love algebra, it incorporates a lot more algebra than just simple plug and chug math. But it's not hard. It's one of those things that seems like there's a lot, and it's a mess, and it's confusing, and it's very formulaic in how you do the problems, and it's really rather straightforward, but you have to do it. And you have to practice it to wrap your mind around it. Anyhow, they're called ICE problems, which is why we have that really bad Ice Ice Baby logo up there. Okay, so here we go. Oh, that looks weird. Anyhow, there's really two types of problems. Here's type number one. And you can see what it says. A student prepared a 0.010 molar solution of hypochlorous acid and found its pH to be 4.73. And what it wants you to do is calculate the Ka. Just like we did yesterday, what's the acid dissociation constant? But the problem is you don't know the concentrations at equilibrium. What you do know is you can write out what the dissociation would be. Here's hypochlorous acid. It dissociates in equilibrium, reaches an equilibrium where you have a certain amount of hydrogen ions and a certain amount of hypochlorite ions. Here's what else we can do, because they always have the same setup. The acid dissociation, the Ka, the equilibrium, then is always the product over the reactants. So it is the ions, the ion concentrations, multiplied together, divided then by the molarity of the solution, okay, at equilibrium. See, we know the molarity before equilibrium, and we're also told the pH, but we don't know these numbers at equilibrium. So there's got to be a way to find them, and that's why it's called ICE. And again, we also know the pH is that. And so since hydrogen ion concentration is going to be a key here, then we used our formulas that we were using in pH stuff to just figure out what is the hydrogen ion concentration, which, if you remember from our pH formulas, is 10 to the minus pH. So I plug it in and I get the molarity is 1.86 times 10 to the minus 5. So that really is just pulling out, what do I know of this problem? Okay. Now notice we haven't used the initial molarity yet, but we at least just converted the pH to hydrogen ion concentration, because looking at this formula, there's probably going to be a reason to use it. Okay. All right. Here's where they're called ICE problems. You set up a table to figure out what would be the concentrations at equilibrium. Okay. And that's why it's called ICE. You have your initial setup, how is it going to change? So and I'll show that in a minute. And what is the concentration equilibrium? All right. So here's what we know. We know all these things again. Okay. And here's how our table is going to be set up. Just like the reaction. Here's our reactant, the hypochlorous acid. It's going to break down into our two products, the hydrogen ions and the chlorine ions. Okay. So then let's start filling out the ICE table. And here's what it looks like. This is where this comes in. I know that when I initially start, as I just put the stuff together, just think the instant that I make this acid, I have 0.01 molar stuff. And I have no ions and no hypochlorite ion. Okay, no hydrogen, no hypochlorite. That would be right initial at the moment. I've just mixed the acid. It hasn't had time to dissociate. Okay. So at that initial instant, it's 0.01 molar compound and 0 of the ions. Okay. But it is going to break down. Now, how much is it going to lose? We'll look to this and think stoichiometry. This is all a 1-to-1-to-1 ratio. Where do these come from? Here. So I'm going to lose X amount of my compound. X amount, just a variable. I don't know the number yet, but X amount is going to dissociate. Okay, makes sense? I'm not going to stay all compound because I've got to move into that equilibrium where I've got some ions and got some compound. So I'm going to lose X amount. Well, where's that X amount of compound going? Well, it's, as I lose X, that means in a 1-to-1 ratio, I'm going to be gaining X amount of hydrogen ions as the compound comes apart, and X amount of hypochlorite ions as the compound separates. Okay. And when we get to equilibrium, those numbers don't change, right? Right? Those numbers don't change. So at equilibrium, it's going to be the 0.01 initial molarity minus however much I lost, okay, whatever concentration dissociated. And the ions are going to be X, the amount that dissociated. Okay. That is the moment. You have to just sit back for a minute here and ponder that. That is where young folks get a little confused at first, and that's what makes it look at that table. It looks all cumbersome and ugly. But all it's saying is I started at 0.01 and some of that compound broke down. How much? That's what I'm trying to figure out. But I know X amount broke down. And what that X amount became was X amount of hydrogen ions and X amount of chloride ions, because they're hypochlorite ions, because they're all in a 1-to-1-to-1 ratio. And so at equilibrium, whatever that concentration of the compound, the hypochlorous acid is going to be my initial 0.01 minus X. Okay. And my hydrogen ion concentration is going to be X, because it's 0 plus X. That's how much I gain. And my hypochlorite ion concentration is going to be X, because it's 0 plus X, how much I gain. Now, here's where we come back here and go, oh, wait a minute. We had the pH. When do you find the pH? When it's at equilibrium. When it's at equilibrium. So here's what I know. I know X because X is this. Since pH is the measure of the hydrogen ion concentration at equilibrium, then I know what X is. Because this is what I want. I want my hydrogen ion concentration. There it is. It's 1.86 times 10 to the minus fifth. Okay. So filling it out then, my X is 1.8. So put 1.86 times 10 to the minus fifth everywhere you saw an X. This was losing that amount, gaining. So at equilibrium, if I take 0.01 and I subtract 1.86 times 10 to the minus fifth, I get 0.00998. Okay. And X becomes 0 plus that number, so there you go. Or hydrogen ions become 0 plus that number, there we go. The hypochlorite ions become 0 plus that number, there we go. Now I can do my math. Now I can just plug the concentration numbers in where they belong and solve. And the Ka comes out to be 3.47 times 10 to the minus 8, which, if you remember from yesterday, definitely tells you it's a weak acid. All right. So that's problem number 1 type. You're given the initial concentration and you're given the pH, and you can use that to solve Ka. Let me give you a second type. What if you want to find a pH? You know the Ka, and you know the initial concentration of 0.5 for this hydrofluoric acid solution, but I want to figure out what's the pH of that solution at equilibrium. Okay. Now, we're going to talk about as we go through this style of problem where you're looking for the pH. Okay. Requires a couple of assumptions. And at the end, something called as you're going, something called the 5% rule. Okay. Which I'll kind of scare you right away. If it doesn't fall within the 5% rule, you get to use the quadratic equation. Hooray! Hooray! Anyhow, some of the assumptions are this. If I look at this acid dissociation constant, look at that small number. Remember, strong acids were things that, rough guideline, were considered over 1 on the Ka. And weak acids, as we talked about in our last video, while again, the guidelines are not set in stone, are things that are lower than 10 to the minus second. So that appears to be a weak acid, which unfortunately means that, you know, the nice thing would be if this was a strong acid, you could just take the 0.5 and negative log and find a pH. But you can't because it's a weak acid. Okay. That goes back to that discussion yesterday that pH is an indicator of acid or base, but not a great indicator of strong acid, strong base, except for strong acid, weak acid, strong base, weak base, except for as the numbers get low enough, it's hard to get a weak acid to have low pH numbers. So as you get below 1 on the pH scale, then you're probably stuck with a weak, strong acid anyhow. And your pH would be the same as the hydrogen ion concentration. That is not your pH, I should say, your pH would be the same as using the initial concentration. That is not true of weak acid. So assumption number 1, looks like a weak acid, so I can't just use the molarity. Okay. So again, it sets up very similar, except now I know the K. Here's my dissociation. Hydrofluoric acid is going to break down into hydrogen ions and fluorine ions, and it's going to hit an equilibrium somewhere. It looks like it's a weak acid, which means it's really mainly going to be compound and very little ion. That was kind of our definition of weak acid, is that it stays neutral compound and very little of it dissociates into the ion. So you don't have a whole lot of hydrogen ions to do acid extravaganza. I then have used that to set up my product over reactant acid dissociation equilibrium, and I've plugged in the number that's there. And again, I've got my ice table with my compound and my two separate ions. All right. So there is some stuff we can fill out here. Same thing. We know our initial concentration is 0.5 and 0 and 0. At that moment, I just mix it up. That's where we're at. I know, again, everything's 1-to-1. So I'm going to lose, and it's going to get to equilibrium, and it's going to get there by breaking down X amount of the compound. So I'm going to lose minus X, some of the compound. So at equilibrium, it's going to be 0.5 minus X. Where's that X going to go as this compound breaks down? Well, it's going to go into the ions. As this separates into hydrogen and fluorine, it means that as I lose X, that means I gain X amount of hydrogens, and I gain X amount of fluorines. So then, really, again, this becomes X and that becomes X because 0 plus X, 0 plus X. Now, problem, unlike the last problem, I don't know the pH, so I can't just find H. I mean, I can. This is what I have to do. I have to figure out what X is. Okay. That's what I have to do. Okay. In the first problem, I was able to just solve the pH for it and plug it in. Ain't quite happening here. So let's go next. To find X, we need to make an assumption about X in weak acids. And that's this. Here's what we know. If this, by its Ka, is a weak acid, then what we know is it's going to be almost all compound. Very little of it is going to break down. Very small amount. Remember what we saw with water dissociation was 1 times 10 to the minus 14. Right? Okay. So very little. Even though this is 7.1 times 10 to the minus 4th, it means almost all compound, very little hydrogen and fluorine. So what's the assumption we can make? You see there, I cross out the X. All right. All right. Because think about it. If I plug this into the, if I go X, X, and 0.5 minus X equals that number, and just go through the math to solve for X, it's going to be a mess because of the 0.50 and all the algebra distribution you got to do. And that's why you would have to plug that in, solve it all, make it equal to 0, and use the quadratic equation. And when you take freshman chemistry, which many of you will as your initial science course in college at any level, you will be doing it. They will tell you the safest way to always do it is use the quadratic equation. But that can be a pain. We know it can be a pain. Okay? So that's why we make an assumption. Weak acids dissociate only really small amounts of compound. Very little compound separates into its ions, which means compared to the 0.5, that X is going to be almost negligible. It's not going to really knock that thing down much. Okay, that's the assumption. Because it's a weak acid, X is going to be a very small number, and that very small number is not going to change because it's a weak acid that stays even at equilibrium, mainly compound, that the small amount of X is really not going to change the 0.5 much, significantly for the math. That it really won't change things significantly for the math. So we cross out that X and ignore it, which then allows us to set up our equilibrium expression, our acid dissociation, as here's my Ka number. And now H becomes, the hydrogen ions become X, that becomes X, and that becomes 0.5 instead of 0.5 minus X, because this is a whole lot easier math. Okay, now I just solve for X. You know, so X times X becomes X squared. I multiply by both sides by 0.5. And then I take the square root and I isolate x and blah, blah, blah. When I do all the algebra, here's my number, 1.9 times 10 to the minus second. Okay. That's my value for x. Now I got that value by making the assumption that I could ignore the 0.5 minus x because it's not going to change 0.5 a whole lot. And so here I don't have to write 0.5 minus x, which would make it a much more cumbersome algebra problem, and I'd have to take the whole thing and do the quadratic equation. This, by making one simple assumption that this small amount isn't going to change that number enough to make a significant difference here, is how I can do it and make the math that much easier. So then I just plug in my numbers. 7.1, xx 0.5, I do the math, I get 1.9 times 10 to the minus second. I did that in the last slide. Since pH is negative log of h, I go negative log of 1.9 times 10 to the minus second, and I get 1.7. So making that assumption that I could ignore writing the x in this portion of the 0.5 minus x, I come out with 1.7. Okay. Now, what's the 5% rule? The 5% rule says I can do that assumption if and only if my x is 5% or less than what the initial concentration was. Okay. So here's the x when I made my assumption and did the easy math. So now I need to take that number, divide by the initial concentration of 0.5, multiply by 100. And it turns out that is 3.6%. So our assumption holds. If we'd done the quadratic equation, our answer wouldn't have significantly been any different. So we don't have to. We can just go with our assumption, which was get rid of x. Okay, and just have it x times x over 0.5. If it didn't hit the 5% rule, then again, you would have to plug in the whole thing as x times x over 0.5 minus x equals 7 point whatever the Ka. You'd have to solve the whole thing out. You get your x squared, you get your, you get your x squared, your x, your number, whatever, and then you'd have to do the whole quadratic equation. Okay. If we were in the classroom, I might go through an ugly one like that with you because we could go slow and I could answer your questions. When we're online, you might get lucky to never have to use it. Might, no guarantee. Anyhow, there you go. I got a acid dissociation little worksheet with just a few problems of these types to have you practice. And that's it. That's what we'll do. So I'm not even going to tell you when that's due. I'm just going to say work on it over the weekend. Don't wait until Tuesday to try and do it all. All right? That's a good place. Hey, have a good, long, restful weekend. I mean, pick away at this stuff. Here it's Friday. Pick away at a little bit. Maybe you can look at a little bit Saturday, Sunday, Monday, whatever. But it's also a time to sit back and relax a little bit, not the whole weekend. Don't ignore all your studies, not just my class, but all your studies. Don't ignore them right now, but make sure you're enjoying some time to relax. We'll see you on Tuesday. Have a great weekend.